Good morning to all. I am Karina from BSc Chemistry Honors second year. Today's our topic is from Pradeep's Inorganic Chemistry book by Dr. K. Bhasin. Our topic is acids and bases. Arrhenius concept of acid and base. Arrhenius, a Swedish chemist, was the first to define acids and bases in aqueous solutions. According to Arrhenius, an acid is defined as a substance which contains hydrogen and which when dissolved in water gives hydrogen ion. Accordingly, all mineral acids like HCl, HNO3 and H2SO4 containing hydrogen when dissolved in water dissociate completely into hydrogen ions, as HCl in the presence of water gives H positive plus Cl negative. HNO3 in the presence of water gives H positive plus NO3 negative. H2SO4 gives 2H positive plus SO4 2 negative. Arrhenius named these acids which dissociate completely in water as strong acids. There are other acids like acetic acid CH3COOH, carbonic acid H2CO3 and phosphoric acid H3PO4, which when dissolved in water do not dissociate completely into ions. As a result, an equilibrium is set up between the ions and the undissociated acid molecule as shown below. CH3COOH is in equilibrium, H positive plus CH3COO negative. H2CO3 is in equilibrium, 2H positive plus CO3 2 negative. H3PO4 is in equilibrium, 3H positive plus PO4 3 negative. Arrhenius named these acids as weak acids. According to Arrhenius, a base is a substance which contains hydroxyl group and which when dissolved in water gives hydroxyl ions. Thus, substances like NaOH and KOH, which when dissolved in water dissociate completely to give hydroxyl ions OH negative, as NaOH in presence of water Na positive plus OH negative, and KOH in the presence of water gives K positive plus OH negative. Arrhenius named these bases which dissociate completely in water as strong bases. There are other substances which do not completely dissociate into hydroxide ions. Arrhenius named these substances as weak bases. For example, substances like NH4OH, MgOH twice, AlOH thrice do not dissociate completely to give OH negative ions and can be written as NH4OH is in equilibrium NH4 positive plus OH negative. MgOH twice is in equilibrium Mg2 positive plus 2OH negative. AlOH thrice is in equilibrium Al3 positive plus 3OH negative ion. Hydrogen ions H positive obtained from the acids and hydroxyl ions OH negative obtained from the bases combined together to form unionized water. Arrhenius described this combination of H positive and OH negative ions as neutralization reaction. For example, NaOH to form Na positive plus OH negative, HCl to form H positive plus Cl negative. On combining these, we get Na positive plus OH negative plus H positive plus Cl negative to form Na positive plus Cl negative plus H2O. Cancelling the common ion on both the sides, we obtain H positive plus OH negative to form H2O. Neutralization. Arrhenius concept is very simple to apply and explains a number of phenomena like neutralization, hydrolysis of salt, strength of acid and bases. However, there are certain limitations which are described below. Arrhenius concept of acid and bases is applicable only in aqueous solution. This concept fails to explain the acid or base behavior of substances in non-aqueous medium such as liquid ammonia, liquid sulfur dioxide, alcohol, etc. Arrhenius concept fails to explain the acidic character of substances like CO2, SO2 and SO3, etc. and basic character of substances like NH3, Na2CO3, CaO, etc. Arrhenius concept also fails to explain the reaction between an acid and a base in the absence of water. For example, NH3 plus HCl to form NH4Cl solid, Na2O solid plus SO3 gaseous to form Na2SO4 solid. NH3 and HCl taken are all gases. are in gaseous state. Although Arrhenius concept of acid and base suffers from a number of limitations, yet the concept is very useful and informative for an elementary approach. Bronsted Lowry concept. Arrhenius concept of acid and bases was further improved by Bronsted and Lowry. For both Bronsted, a Danish chemist, and Lowry, an English chemist in 1923, incidentally introduced the same definition for the acid and bases. According to Bronsted-Lowry concept, an acid is a substance which can donate a proton H positive, whereas a base is a substance which can accept a proton H positive. In other words, an acid is a proton donor, whereas a base is a proton acceptor. As a result, Lowry-Bronsted concept is sometimes called the proton donor acceptor concept. It can be represented as acid 1 is in equilibrium H positive plus base 1 proton donor. Base 2 plus H positive is in equilibrium acid 2 proton acceptor. According to Bronsted-Lowry, a neutralization reaction involves the release of the proton by an acid and the acceptance of that proton by a base. For example, the reaction between HCl and NH3 to form the salt ammonium chloride can be represented as NH3 plus HCl is in equilibrium NH4 positive plus Cl negative. The curved arrow showed how electrons must rearrange to result in the transfer of hydrogen atom from the acid to a base. The unshared pair of electron on the nitrogen of ammonia is attracted by the partial positive charge on the hydrogen in the polar hydrogen chloride molecule. A comparison of the structures of these reactant and the products shows that the hydrogen atom which was bonded to chlorine in the reactants is bounded to nitrogen in the product. Thus, a proton has been transferred from chlorine to nitrogen to act as a Bronsted-Lowry base, a species which must have at least one unshared pair of valence electron so that it can form a covalent bond to the proton. To act as a Bronsted-Lowry acid, a species must contain at least one hydrogen atom that is attached to an atom that is more electronegative than hydrogen. In this case, HCl loses a proton and it is an acid. Ammonia accepts a proton from HCl and is a base. Some other example of acid-based reactions according to Lowry-Bronsted concept are HCl plus H2O equilibrium H3O positive plus Cl negative. Acids are proton donor and bases are proton acceptor. H2SO4 plus H2O to form is in equilibrium H3O positive plus HSO4 negative. H2O plus NH3 equilibrium NH4 positive plus OH negative. It is important to note in the above example that water acts as a base with respect to hydrochloric acid and sulfuric acid. Interestingly, water acts as an acid with respect to ammonia. Such a substance which acts both as an acid proton donor as well as a base proton acceptor is called amphoteric or amphiprotic substance. Similarly, bicarbonate ion HCO3 negative behave as an acid and a base. HCO3 negative aqueous plus NH3 aqueous equilibrium NH4 positive aqueous plus CO3 2 negative aqueous. HCl aqueous plus HCO3 negative aqueous is in equilibrium H2CO3 aqueous plus Cl negative aqueous. Other example of amphoteric substance is hydrogen sulfate ion HSO4 negative. Conjugate acid-base pair. Let us reinvestigate a reaction between an acid and a base. HCl plus NH3 is in equilibrium NH4 positive plus Cl negative and all are present in the aqueous state. HCl being an acid donate a proton and form Cl negative ion, whereas ammonia being a base accepts a proton and form ammonium ion NH4 positive. Now the chloride ion Cl negative has a tendency to accept the proton, whereas ammonium ion NH4 positive has a tendency to donate a proton. In other words, an acid donates a proton and becomes a base, and a base accepts a proton and becomes an acid. Thus, a base formed from an acid is regarded as the conjugate base of the acid. Similarly, the acid formed from a base is called conjugate acid of the base. In the example above between HCl and NH3, Cl negative is the conjugate base of HCl and NH4 positive is the conjugate acid of the base NH3. Acids and bases that are related by the loss or gain of H positive ion are called conjugate acid-base pair. Thus Cl negative and HCl, NH4 positive and NH3 are conjugate acid-base pair. We can represent the acid-base pair as acid equilibrium, conjugate base plus H positive ion, base plus H positive ion, equilibrium, conjugate acid. It clearly indicates that any acid-base reaction would involve two acids and two bases. These acids and bases are called conjugate pairs. For example, acid 1 plus base 2, equilibrium acid 2 plus base 1. That is, for example, HCl plus H2O, equilibrium H3O positive, conjugate acid plus Cl negative, conjugate base. In the above example, HCl is an acid since it donates a proton and Cl negative is its conjugate base. Accept the proton and hence is a base. Water accept the proton and hence is a base. Thus H3O positive ion is the conjugate acid. A strong acid has a weak conjugate base and vice versa. Some other example of conjugate acid-base pairs are cited below. Conjugate pair, HNO3 plus H2O, all are in the equilibrium state. H3O positive plus NO3 negative. HCN plus H2O equilibrium, H3O positive plus Cn negative. H2O plus H2O equilibrium, H3O positive, OH negative. CH3COOH plus H2O equilibrium, H3O positive plus CH3COO negative. HSO4 negative plus H2O equilibrium, H3O positive plus SO42 negative. H2O plus CO32 negative equilibrium, HCO3 negative plus OH negative. NH4 positive plus S2 negative equilibrium, HS negative plus NH3. NH4 positive plus H2O equilibrium, H3O positive plus NH3. It is further important to note that the Bronsted Lowry concept is not restricted to only neutral molecules. The concept is equally applicable to ions as well. A careful inspection of the above discussion reveals that a substance is capable of showing acidic character only if the other substance is capable of accepting the proton that is a base. For example, HCl is an acid in aqueous medium because water can accept the proton from HCl. However, HCl is not an acid in benzene because benzene does not accept H positive ion from HCl. Not only neutral molecules but cations and anions may act as acids or bases. Both Arrhenius and Bronsted Lowry concept require an acid to be a source of proton. Thus, all Arrhenius acids are Bronsted Lowry acids. According to Arrhenius, a base is a substance which gives OH negative ions in solution. NaOH in the presence of water gives Na positive plus OH negative. Whereas according to Bronsted Lowry, a base is a substance which can accept a proton. For example, CO32 negative carbonate ion plus H positive to form HCO3 negative bicarbonate ion. Carbonate ion CO32 negative cannot give OH negative ion in aqueous solution. It therefore cannot be an Arrhenius base. Thus all Bronsted Lowry bases are not Arrhenius bases. Limitations of Bronsted Lowry concept. Although Bronsted Lowry concept could explain the shortcomings of Arrhenius concept, yet it could not answer some of the well-established reactions. For example, it cannot explain the reaction between acidic oxides like CO2, SO2 and SO3 with the basic oxides like CaO, BaO and MgO, which takes place even in the absence of water. For example, CaO plus SO3 to form CaSO4. Clearly, in the reaction between CaO and SO3, there is no proton transfer involved in the reaction. The acidic nature of compounds like BF3, FeCl3 and AlCl3. Thank you.